Okay, good evening, all of you. So, today our topic in the probability is MGF, the moment generating function and the characteristic function. So, first I will talk about moment generating function. So, we have seen that moments of a probability distribution play an important role in determining important features of a given distribution. Also, in some cases, it is possible to find the distribution function of a random variable x if all the moments of x are known. Realizing the importance of the moments of a distribution, we attempt to find a function which gives all moments of a given random variable. Such a function will be called a moment generating function. So let us have the definition in the formal way. The moment generating function of a random variable x is a function. It is denoted by mx, m suffix x, from a to r, real number. It's a real valued function. A is a subset of R, defined by mxt is equal to expectation of E for expectation. Already we defined the expectation in the previous class. Expectation for the discrete distribution, expectation for the continuous distribution. So expectation of e to the power tx, provided the expectation exists for all t belongs to R. So this is your moment generating function. And you know that expectation of tx can be expanded in a series expansion, exponential. This is your exponential series. So you can write in this form. Also, for t equal to 0, it will be expectation of 1 equal to 1. So certainly mt exists for t equal to 0 and m0 equal to 1. Okay. So moment generating function is defined by, it's a simple expression, expectation of e to the power tx. Now, for case 1, discrete random variable, how will you write? You know that for a discrete set of values, a spectrum is given by x minus 2, x minus 1 and so on. And probabilities are given by probability x equal to xk, if k. That already we have explained in our probability check classes. The moment generating function of x is given by summation k equal to minus infinity to infinity e to the power txk fk. Okay. That is your from the definition of expectation actually. And replacing x by e to the power tx, that is from your definition of expectation. So it's a simple expression. This is the expression for moment generating function of x in case of discrete random variable, provided the series is absolutely convergent. Okay. Now, we assume that the above series can be differentiated term by term any number of times with respect to t in the domain of definition of m. Then differentiating r times, we get this expression dr ddtr mt at t equal to 0. You will get alpha r. Alpha r is the rth moment about the origin. And also in the previous class, we talk about the moments, raw moments, central moments, and their relationship, skewness, kurtosis. So alpha r denotes the rth moment about the origin. So that is alpha r. So there is a relationship between moment generating function and a moment. There is a connection. Case 2, if you are talking about a continuous random variable, x is a continuous random variable whose probability density function is given by fx pdf. You know the term pdf is used for the continuous random variable. The moment generating function will be an integration. This is the definition of moment generating function. It is from the definition of expectation e to the power x. X is replaced by e to the power 2 tx. So it's integration minus infinity to infinity e to the power tx fx dx, provided the integral is absolutely convergent. Okay. So this is the definition for expression for continuous random variable, and this is the expression for discrete random variable, moment generative function. Okay. Now, also in the continuous case, you can write this is alpha r ddt dr dttr mt at t equal to 0 is related to alpha r. This is the same notation. So the conclusion is that mt, the moment generative function, can be expanded in a power series in T. This is the power series, which indicates that this is the expression. So which indicates that the rth order moment of x about the origin, rth order moment of x about the origin is the coefficient of t to the power r by factorial r in the expansion of mt as a power series in T. As a power series in T. So that is the important conclusion. Mt can be expanded in power series. Now, next we'll define characteristic function. So what is the characteristic function? And we will give you the examples also. The characteristic function of a random variable x is a complex valued function of a real variable t, denoted by phi t or phi xt, and defined by phi t equal to expectation of e to the power itx, expectation of cost. You know that Eulerian expression from the complex number e to the power itx can be written as cos tx plus I sin tx. I is a iota root over minus 1. So this is the definition of characteristic function. Characteristic function is a real valued function. It's a complex valued function of a real variable t. And what is the existence? If you talk about the existence, in the discrete case, you can write the summation k equal to minus infinity to infinity modulus of this and modulus of fk, and this modulus is 1, modulus of cos tx plus I sin txk is 1 because it will give you the 1 value. So this summation will be 1, and so the series is absolutely convergent for all real t. Hence, phi t exists for all real t. This is the discrete case. You can check that for discrete case, it is exists for all real t, all real expression t. And you know that discrete distribution, the properties of discrete distribution gives you the summation will be 1. And in the continuous case, there must be an integration sign. And in the continuous case, modulus of this is 1 and modulus of fx dx equal to 1 minus infinity to infinity because of the properties of the continuous random variable. And so the integral is absolutely convergent for all real t. Hence, phi t exists for all real t because absolutely convergent is the condition for existence of that type of series and integration. So this is for the continuous case, existence, and this is for the discrete case. Now, let us state without a proof a uniqueness theorem. The distribution function is uniquely determined by its characteristic function. If f and phi respectively be the distribution function and the characteristic function of a random variable x, then at each point of continuity of fx can be written as in this expression 1 by 2 pi limit a tends to minus infinity, limit b tends to infinity. That is minus infinity to infinity I am writing e to the power minus ita minus e to the power minus itx by it phi xt dt. This is the uniqueness theorem. So I am stating the theorem without any proof. So I am stating the theorem without any proof. Okay. Next theorem, for a continuous random variable x with probability density function f and characteristic function f. So in this theorem, your fx, the probability density function, is related to characteristic function. You can determine the distribution density function pdf if you know the characteristic function 1 by 2 pi and integration over minus infinity to infinity. This expression is the phi t is the characteristic function. So this relates your probability density function with the characteristic function. And there is a theorem that if you use the transformation y equal to ax plus b and phi x phi y are the characteristic function of x and y respectively, then phi y t equal to e to the power ibt into phi x at. That is your phi y, that is the characteristic function of y, and phi x, that is the characteristic function of x, is related by this relation. This is the relation if you take a transformation. Another relation, phi t, phi of minus t is phi bar t, that is a conjugate transformation. This should be your, this is a printing mistake, typological error. So it will be phi t and this is also phi t. If fx equal to 1 minus f of minus x minus 0, these are all proofs. You can use the proofs of the previous distribution function theorem. You can prove this. So these are the important theorems without any proof. Now let me show you some important results. What is the moment generating function of a binomial distribution? You know that binomial distribution, the PMF of the binomial distribution is NCI p to the power I q to the power n minus I. So using that result, the PMF binomial distribution is a discrete distribution. The moment generating function of x is e to the power expectation of e to the power tx, and that is written as k equal to summation k equal to 0 to n e to the power tk nk. This is the binomial expression. Now you can write p to the power k and n to the power tk in this combined form. Look at that, p e to the power t whole to the power k, and it can be written as p e to the power t plus 1 minus p whole to the power n. That is from binomial expansion. You are using the binomial theorem. So that can be written as p e to the power t plus q whole to the power n, because q is your 1 minus p. So this is your moment generating function of the binomial distribution, which is a function of t. This is your moment generating function of a binomial distribution. Now let us calculate the characteristic function of a binomial distribution. Similar calculation. In this case, your characteristic function, there is a complex valued function itx e to the power itx, expectation of e to the power itx. So e to the power, your x is replaced by e to the power itk in the expectation definition, and this is your binomial distribution. Again you are writing p e to the power it whole to the power k in the combined form, and you are using the binomial theorem. Hence the result will be like this, p e to the power it plus q whole to the power n. This is the characteristic function. Look at that, it's similar to your moment generating function, but only difference is that there is a I. Otherwise everything will be, so it's very easy to remember. You can remember very easily. Okay, so this is your result. Now let us calculate for Poisson distribution. And you know that Poisson distribution is also a discrete distribution, and it's infinite, countably infinite number of spectrum points. So it can be written as expectation of e to the power tx. So again writing in the form of exponential series. So this is the form of the exponential series, and finally you have this expression using the exponential series concept, e to the power mu e to the power t minus 1. So this is the moment generating function of a Poisson distribution. So now you want to calculate the characteristic function of a Poisson distribution. Only difference is there will be one I. All the calculations are same. So you have, look at that, you can check that this is the calculation for phi t, that only difference is I. Okay, complex valued function, this is characteristic function. So this is how you can calculate the moment genetic function, characteristic function. So I am giving you two assignment for all of you. Calculate the, this is my assignment for all of you. Calculate the moment genetic function and characteristic function for normal distribution. Normal distribution, that is a continuous distribution. Okay, you have to calculate the moment genetic function and the characteristic function for the normal distribution, that is a continuous distribution. This is the assignment for all of you. So this is the video about your moment genetic function and the characteristic function, most important definitions, and you can generate the moments from the moment genetic function, and we'll solve the problems in the next class so that you have an idea about the how to calculate the expectation, moment genetic function, and some important theorems we have discussed in this lecture. Okay, that's all for today.